Hi class, welcome back to multivariate calculus. I was originally going to do this lecture, just these two lectures as one, but I started to lose focus and now I'm splitting them into two. So let's keep going, looking at a conservative vector field. So here's the definition of a conservative vector field. If there exists, so this backwards E stands for there exists, and that's a notation that you often use in proofs. If there exists some function f, and this lowercase f is what is called we're going to call a potential function for our vector field, capital F, such that the vector field is equal to the gradient of our function, then we have a conservative vector field. And I'm missing a parenthesis here. There we go. So let's look at the gravitational field for an example. So our gravitational field is given by minus lowercase m, and this lowercase m is the mass of the smaller body. Uppercase m is the mass of the heavier body, and capital G here is the universal gravitational constant, which is different from little g. Little g is the acceleration due to gravity, which varies depending on where you are, and big G does not. Big G is an absolute constant. Okay, times the vector x divided by the magnitude of x cubed. Now let's think about this for a sec. So the gravitational field is a force field, and in metric, the unit for force is Newton. So I'm going to write this down here just to kind of keep track. The metric unit for force is the Newton. And if we look at the potential, the gravitational potential, as a function of x, y, and z, so these equations, I think, are much more straightforward in spherical coordinates, since the gravitational field is a force field that's spherical. So like in terms of r, where remember r squared is equal to x squared plus y squared plus z squared. And so here, this potential function, f, is going to be gravitational potential. And the equation for gravitational potential is little m, big M, g, over the square root of x squared plus y squared plus z squared. So gravitational potential is energy. Energy is not a vector, and the metric unit for energy is a joule, and a joule is equal to a Newton meter. And so if you were going to do dimensional analysis on this, what you end up is, well, if you canceled out this vector x with one of the vector x's down here, you end up with mmg over a distance squared. And if you did dimensional analysis in metric units, that would come out to a Newton. And here, you're dividing by the square root of x squared plus y squared plus z squared. And remember that in this case, x is equal to the square root of x squared plus y squared plus z squared. So dimensionally, they come out the same. Well, this comes out as Newton meters equivalent, or energy, which is joules, and this would come out as newtons. So aside from dimensional analysis, and I'm not going to go through that whole piece right here, what I want to do is I want to take the gradient of our potential function. And the gradient of our potential function is going to be the following. So first, we have to take the partial derivative of this function with respect to x to get the x component. And so we could also write this denominator here as x squared plus y squared plus z squared to the 1/2. We could bring it to the numerator, right? And we could write this as mg times x squared plus y squared plus z squared to the -1/2. All right, so that's a little easier to look at. And so if you were to take the partial derivative of this with respect to x, it would be, well, we have a minus sign here, it would be minus mg. And so then if we did this outer portion, we'd have to subtract off 1/1 or 2/2, and we end up with -3/2. And then we have another x lingering. So we end up with, and we have a half, and then we have 2x, so 1/2 and 2x cancel out, and we end up with x squared plus y squared plus z squared to the 3/2, and we still have an x, and that's our I hat component. So to go through this one more time, right? So we would have, if we took the partial derivative, we'd have -1/2 mmg x squared plus y squared plus z squared to the -3/2, and then we have the product rule, or the chain rule, and so then we have to take the derivative of this interior with respect to x, and that's 2x. 2 times 1/2 gives us x. Okay, so that's where that part comes from. And it's going to look, it's going to be analogous for our y and z's. So minus mm gy j hat over x squared plus y squared plus z squared to the 3/2. And then we have our z component, which is going to be minus g z k hat over x squared plus y squared plus z squared to the 3/2. And we could rewrite this as minus g. Remember, vector x is going to be, vector x is x I hat plus y j hat plus z k hat. Okay, so we can write this whole thing, x I hat plus y j hat plus z k hat, as vector x divided by, well, the square root of x squared plus, so x squared plus y squared plus z squared to the 3/2 is the same thing as taking the magnitude of x, which is the square root of x squared plus y squared plus z squared, and cubing it. So this tells us that f is equal to the gradient of our potential f. So therefore, the gravitational field is a conservative vector field. Okay. So we'll keep practicing with this a little more in upcoming classes, but if there exists some potential function where if you take the gradient of that function and you get the vector field equal to that gradient, then it's conservative. Now let's do one more together. the flow of lines or streamlines of a vector field path are paths followed by a particle whose velocity field is the given vector field. Thus, the vectors in a vector field are tangent to the flow lines. So we want to sketch f of x and y is equal to xi hat minus yj hat to draw some flow lines. And then we're going to guess the equations. And if we were in class together, this would be a bit more interactive, but it is what it is. So if we were going to just like sketch out xi hat minus yj hat, we'd end up with level curves that look something like this. And the flow would be something like this. And let me just open this up once again in Academo, and we'll take a look at it. So looking at our course, under our free 3D visualization section, if we go to Academo, and we go down to the vector field plotter, we can just plot this vector field, which was x I hat and minus y j hat. All right, and so what you can see is we have our vectors, okay? So you can see the direction of flow. So we're flowing out this way, this way, this way, this way. And so what does this plot look like? What equation looks something like this? And so I want you to pause it and think about it. And when you're ready, resume. But the equation that looks something like this plot is going to be y is equal to some constant over x. That's what we're looking at there, right? So if the parametric equations of a flow line are x is a function of time, y is a function of time, explain why these functions satisfy the differential equations dx over dt equals x and dy over dt equals minus y. And then solve the differential equations to find an equation of the flow line that passes through 1, 1. So what we're looking at is the derivative with respect to time is x. So with increasing time, we're heading towards x. And here, the derivative with respect to time is minus y. And so for y, we're heading opposite direction. So when y is positive, we're heading down, and x is still heading in its normal direction. When we're at positive y, we're heading down, so that's the opposite direction. And x is minus x, and so we're still heading in the same direction, minus, minus, okay? So it's like the same sign. And so over here, we're doing opposite sign for the y. So as we get more negative, y is getting more positive. X, it's the same direction. So as we get more negative, we get more negative. And so we want to know, we want to find an equation of the flow line that passes through 1, 1. Well, we already determined that y is equal to a constant over x works for this. And so I want you to find a case in which the flow line passes through 1, 1. And this is one of those cases where it's a little more straightforward than it seems. And quite simply, y is equal to 1 over x, where x is greater than 0, so you can't have 0 in the denominator. It's going to give us, if we have x equal 1, we get y equals 1 out. So that would be an example of an equation of the flow line that passes through 1, 1. So as with anything in calculus, the more you practice, the better you get at solving these problems. And if you have any questions on the content, please reach out to me and I will be happy to clarify. So take care, and I will see you next time.